Hello, and welcome to this PowerFilm and EPs webinar. And now I would like to introduce today's presenters. With us today is Sam Jones. Sam is a research and development engineer at PowerFilm. And joining Sam today is Sarah Houghton. Sarah is a senior field application engineer at EPs. To read more about the speakers, please take a look at the speaker bio area next to the right of the main presentation window. Now, Sam and Sarah, welcome to today's event. And with that, I'd like to pass things along to Joe Ward to get this presentation started. So, Joe, go right ahead.
Thank you, Katie. Thank you, everyone, for attending our webinar. We're really excited to be able to present to you today, and I'm excited to have one of our key partners in the energy harvesting ecosystem joining us today on this session. This is really exciting for us. We've got 500 people signed up for this webinar. It just shows you how people are very interested in energy harvesting. It's been around a while, but there's been a lot of innovation lately, and that's what you're going to see through the course of this presentation today. And it's making it a very viable option for replacing batteries and extending battery life in any type of battery-operated device. On the slide, you see the name of our company, EPs. Everybody asks me what it stands for. It's Electronic Portable Energy Autonomous System. We're headquartered just outside of Brussels in Belgium. We're a small startup, but growing fast. We're fabless. We use one of the biggest foundries in the world, TSMC. We are all about low power, and we're really focused on energy harvesting. So a couple quick things. If you haven't seen our website, I encourage you to check it out. You've got a lot of additional information than what you'll see today on the website, and plus access to data sheets, app notes, and details on our evaluation boards. Also, there's a listing of all our sales reps that we have around the world, so you feel free to contact them for any assistance or just contact EPs and we'll be able to help you out. Our eval boards are available through purchase through DigiKey, and all of our products are available through Mouser and Fujitsu Electronics. So if you have any interest in that, you feel free to look them up. And again, if you have any questions, please contact us and we'll coordinate however possible. So that's my quick introduction. I'm really excited to turn this over to Sarah to start the main presentation. Sarah?
Hi, thank you, Joe. So welcome everybody. I'm Sarah, working as a field application, and today what we will learn is energy harvesting. But first question, why looking for energy harvesting? As you may know, the optimization of each device consumption and the power management cause headache to end user and the industry. How should you best improve your device feature, and how about changing battery each day or get it recharged? How can you estimate the real lifetime? How can you extend it in order to remove the maintenance cost? How much is it going to cost you changing the battery, and actually who's in charge of replacing the battery? Which feature should you implement? What the battery size? How to optimize everything? And actually, energy harvesting is a solution to all those problems. It provides you energy every day to supply directly your device and remove the maintenance issues. But how does it work, and what do you need actually to get energy from the ambient sources? First, what you will need is an harvester to transform the energy into electrical power. And you will also need a storage element, actually a rechargeable one, that you can use to store energy for later use, like a sensor measurement or radio communication. In this webinar, we will focus on indoor and outdoor lights using our partner's PowerFilm PV cells. Energy harvesting required an AEM. This is our PMIC project, Ambient Energy Manager, and it's placed between the harvester and the storage. But we will now look at why do you need an AEM for PMIC in between the harvester and the storage. The two first reasons are about the harvester. We will actually take care of extracting the maximum power from the harvester, and also we will take care of the cold start, meaning that we will enable the system so the AEM will start alone. It doesn't need any other supply. As soon as we have 300 megawatt, 380 millivolts, it will get started and it will collect the energy. It will also take care of energy transfer, efficient energy transfer in between the source, the storage, and actually your hardware device you would like to supply. And finally, it will take care of the storage element, meaning it won't get it overcharged or over discharged, and everything is included in the AEM. But how do we ensure that we extract the maximum power? Actually, we use a MPPT, so it's a maximum power point tracking. If we look at the power versus voltage curve of a PV cell, for example, here in green you can see the power versus the voltage. If you look at this curve, where you would like to work is at the maximum point, being there at a defined voltage. This means that you would like to work at a defined voltage here called VMPP. All harvesters actually show a maximum power curve, so it's at the bottom of the curve, and it could vary with the environment. So if you have a light change or any other changes in the environment, you will see that the working point, so the voltage you should work at, will change. And the AEM will take care or actually adapt its working voltage to ensure you that we are always working at the maximum power point. If you don't do that, actually you are not able to extract the maximum power from the environment. So here, if we have the second curve, the curve 2 in orange, it's meaning you have less light. What you need to do to still be working at the maximum point, it's not work at VMPP1 voltage, but VMPP2. And how do we do that? Actually, we measure the open circuit and we apply a ratio. This MPPT ratio is something related to the harvester technology. This is something you will find in the PV cell data sheet. And as soon as you configure correctly the AEM, at a constant interval, the AEM will get disconnected from the harvester in order to let it achieve its open circuit voltage. Then it will get back connected again. Time it's disconnected is about 1% of the time, and as soon as it gets connect again, we'll measure the open circuit voltage, apply the ratio, and get its new working voltage. For the life of the AEM 10941, which we recommend to use with the PV cell of PowerFilm, we adapt this working voltage each 5 seconds. And just an example of what is happening, if you actually don't define the right MPP ratio. So let's take here an example of working at 75% is the optimal, but you define 90% by configuration of the AEM. It's just that you won't be able to extract the maximum power from the ambient. So it's quite important to be sure that you select the right MPPT ratio. About the AEM behavior, how does it actually behave? If we start from deep sleep mode, so meaning you have no light, as soon as we have enough to get started, so it's 3 microwatt, 380 millivolts, then we will wake up. You will first have an internal node VBUC rising up to 2.2, and at that moment we will actually transfer the energy from the source to charge the storage element. So if you try it and you buy our eval kit and you start looking and using the AEM 10941, you will see your VBUC node rising up, so the storage element voltage. And there we have different options. As soon as we enter the normal mode, meaning that we are transferring energy from the source to the storage, there are some protections. The first protection is if you achieve the maximum voltage on the storage element, then we will switch off the boost. You could also reach out the minimum level defined, and there you could be using a primary battery. So if you connect the primary battery, it will be used as a backup solution if you achieve the minimum level. But if you didn't connect any primary battery, or let's say it's already discharged, then we will rise up a status to prevent the application that we will shut down the LDO. And we will actually switch off the internal LDO, meaning that we won't supply your application then for the storage element protection. So those are the storage element protection integrated in the AEM. So Here you can have a look at the table, which is available in the data sheet, which allow you to define the storage element protection level. So you have 7 predefined protection level and actually 1 custom mode, which could be used if you would like to define your own protection level. You also have 3 stages telling you if you achieve a certain level on the storage, which are stages 0, stages 1. And just here you can see the different configuration you can define using the AEM. So the first option we recommend you to use with a Li-ion battery. You can see here in yellow the different voltages you actually will getting out of the AEM. So I'm sorry I did not mention it, but actually we have internal converter integrated in the AEM, which are providing you regulated output voltages. Here VHV or VLV, so you have 2 options that you can either disable or enable. If you enable, then you will have a 3.3, 1.8 or 2.5, depends on the configuration you choose, but you will have well-regulated voltages to directly supply sensor, radio, microcontroller, anything you would like to supply. And if you don't, if you are using a supercap, we actually have specific balancing circuit if you are using dual cell supercapacitor, but here you can see 3 options for the storage if you are using a supercap, which will allow you to use a single cell that we will charge up to 2.7, discharge to 2.2, and you will get 1.8 on HV out and 1.2 on LV out, so VHV, VLV. And you have 2 options for the dual cell supercapacitor, providing you either 3.3 or 2.5 on VHV. If you don't want to use those predefined configuration mode, then you can use the custom mode, which needs 6 additional resistors, but you can define your own overcharge, over discharge level protection, and also the VHV voltage you will get out from the AEM. So this is the entire family. You have the AEM 10941 we recommend to use with photovoltaic sources, the AEM 2940, which is mostly used for thermal, and you have the AEM 3940 that you could use with AC sources. But here let's focus on the AEM 10941 used with our PowerFilm PV cell. One big question is, how do I start to integrate energy harvesting in my device? What we recommend you to look at is first what you would like to supply. What's the sensor MCU or radio you would like to supply, and what's their consumption? As soon as you have an idea of the consumption of your application, you can estimate the energy you need to boost out of the AEM, actually boost in the storage element, and having an idea of when the light source is available, you can estimate the power source you need to get from the PV cell. And there you can also estimate the energy you need to store for the time you don't have power. So let's say for a day you have 8 hours of light, you have 16 hours without any light, and you have to store energy to supply the application for those 16 hours. And this is how you can start, let's say, sizing the element. You have an idea of the power you are looking from the PV cell, an idea of the light you will have, and this is quite helpful to size and choose the right PV cell. And knowing how much energy you would like to store, then you can size the storage element, either a supercap or battery. So those are the different questions you should ask yourself before starting. You can also contact us and we will help you to size the different elements. And those are the different questions we will ask you about the consumption of your load, what different voltage you require, do you have any current bit, which is quite important to know, size correctly the storage, do you need any backup solution? As I mentioned, we have the primary battery option. What autonomy do you need? It's quite important also to size the storage, and which environment and when the source is available. This is quite important also to discuss with PowerFilm and size correctly the PV cell you should be using for your application. And as soon as you have all those questions answered and an idea of what should be tested, then you can start using our eval kit. As Joe mentioned, we have devices available on Mother, some eval kit, but we also have an eval kit dedicated for with our partner PowerFilm. So you can use it. You can connect the PV cell from PowerFilm. You can connect the storage element. So it could be either a supercap, you have a footprint in the bottom, or battery, and you can directly supply your application with the LV output voltages you got out, so LV out here and HV out. So this is the kit, and if we open the box, we will move on to PowerFilm's part, and I think we will continue first with Kip and then with Sam.
Hi, Sarah. Thank you. So this is Kip Johnson from PowerFilm. Also, I want to thank everyone for taking the time to attend today. We're excited to work with EPs as a partner and to present energy harvesting solutions and capabilities. PowerFilm is a manufacturer of solar material. We work with a couple different kinds of solar material. Our film material, shown in the top picture on this slide, is a very thin, very flexible, very durable material. We also work with traditional crystalline cells, which are shown in the picture. The film material we manufacture ourselves in-house. We're a US-based manufacturing company, and because we control the manufacturing process, we can make those cells in most any physical dimension and most any voltage required for your applications. And so our business is really sort of three segments: a military business and then a custom solution, really targeting at commercial and industrial applications. The film material will work, as I think Sarah had alluded to, in indoor as well. Of course, the power requirements or the power available for indoor light is much less than outdoor light, but Sam will walk through a variety of applications there. So again, I want to thank you for taking the time out of your day to attend the webinar, and I'll turn to explain some of the PowerFilm capabilities.
Hi, thanks, Kip. My name's Sam Jones. I'm a research and development engineer here at PowerFilm, excited to kind of show you guys and what we do in the energy harvesting space and how our material and PV cells apply to some of the applications you might be looking at. I like to start out with this slide, and it really puts energy harvesting kind of in explains it in a tangible way. So asking the question, what can I actually power with solar harvesting? So if I have a solar panel on, say the one on the left here is LL200-337, that's one of our standard panels. What can I actually power with that panel? The answer to that question, I think, depends on three primary things. Where that device is located, the device you're actually trying to power, and then the operation of that device. So many IoT devices and electronics, they can be configured in a really, really wide range of areas. In this example, we'll show Bluetooth Low Energy, since it's a very, very common protocol used in a lot of IoT devices. It can be configured ultra low power, but it also has some higher power consumption modes. So it's a really great example to show the wide range of things you can do with energy harvesting. So if I take this panel and I in an indoor space, I put it underneath a desk, it's going to be, obviously very dim environment, but we will still be able to extract, even in a dim environment, some energy, and we can support a Bluetooth sensor, and maybe it can't support a standard connection, but maybe we can update that every couple minutes. Take that panel and put it on top of the desk, a little more light available. Now we can start looking at higher power consumption modes of that Bluetooth sensor. We can actually support a real Bluetooth connection that updates data once a second. If you take the panel and get closer to, say, like a window, even a brighter environment, maybe we can update 10 times per second. If you take the panel and you go outside, it's even brighter. Even if you're in the outdoor shade, we can start looking at turning that Bluetooth device into a gateway. Maybe you're starting to connect other devices around it into a little system. You may not have enough power to run that all the time, but you could start playing around with some partial duty cycle stuff. And then finally, if you point that panel directly to the sun, you'll get the most power out of the panel, and you may in fact get enough power to run that all the time. So that kind of gives you a good idea of just the wide range of power generation from a panel, and then the wide range of configuration that you can get in all these IoT devices. And it's extremely important to understand both the location of where you're operating and then both the power consumption of your device. Both are very important. I mean, it can be thousands of times less power, but that even at that low power level, you can still do useful things. So when I talk about energy harvesting and light energy harvesting, it's kind of good to define what the difference is between traditional outdoor solar applications, which are optimized for solar spectrum and outdoor lighting, versus kind of when you think about energy harvesting and indoor light. So in the next two slides, I kind of break it into a primary factor and then a secondary factor. So when you talk about the difference between indoor and outdoor light, the biggest factor is intensity. So my first point here is power generation changes linearly with light intensity. I mean, if you look at the charts on the right side, you can see that as the light level or lux decreases, the power generation from the panel also decreases. And in parentheses, I say ideally, because my second point is that minor material defects in the panels that you wouldn't normally see under normal conditions and direct sunlight, they become increasingly significant at lower light levels, especially indoors. So a lot of traditional solar panels that are not made and manufactured to be used in lower light environments, those material defects can actually render the panels kind of inoperable. So that's a lot of the customers that we work with. I recommend doing something, or I recommend considering orientation and installation agnostic. I don't know if I coined that term, but I like to use it. Just being able to install your panel into any orientation, whether that's indoors or outdoors, and not worrying about making sure that panel is facing the sun. So we have some customers that come to us and say, I have a device and I want to install it outside, but I don't know if it'll always be illuminated from the sun. It may be on a north-facing wall. So what I like to do is say, okay, well, this is the light level that you can expect in that environment, and then this is the power that you can expect to be generated from the panel, and then you can use that to drive your design decisions. So when you're sourcing a PV or you're looking into different PV options, you want to make sure that the PV cells, the PV that you're going to use is rated for what you would consider your worst case light level. And that's something that is a major benefit of PowerFilm's products. We do have that indoor solar product line, and we guarantee that it works down to 200 lux. And then our outdoor products, we guarantee that they work down to 25% of direct sun. But if you have a custom environment, so say that north-facing wall in Europe, we can kind of work with you to define a custom light level and guarantee that any solution that you have will work in your environment. And secondarily, spectrum will affect the power output of a panel. So different PV technologies that are in different configurations, they may have different material properties, different absorption properties. They will react differently to different light spectrums and light sources. So on the right, you can see that I show the power generation for three common solar technologies under an LED spectrum, and then on the bottom, you can see the performance under an incandescent spectrum. So under LED, amorphous silicon actually outperforms crystalline silicon and triple junction gallium arsenide. And then under an incandescent spectrum, that behavior is somewhat flip-flopped, where the crystalline silicon outperforms the amorphous silicon in the gallium arsenide. And it's also interesting to note that gallium arsenide, if you're familiar, is actually a very, very high efficiency PV technology that under a solar spectrum would outperform any of these technologies. But since it has multiple junctions, multiple layers that are all tuned to absorb a specific wavelength, when you take that wavelength away, that PV module all of a sudden does not perform very well. So you want to make sure that the PV that you source is rated and optimized and will work for whatever spectrum that you expect in your environment. And finally, related to spectrum, you're going to hear me talk a lot about lux level in this presentation. And the reason that we use lux is because that is the industry standard for brightness. But actually, it's a pretty ambiguous measure of power density or photon density, which is really what a solar panel cares about when you're talking about power generation. How many photons is it absorbing to drive that current? So you want to understand the correlation between lux and the power output of the panel. So on the bottom left, you can see the color response of a lux meter. So if your light source is green light, your power density at 200 lux is going to be a lot lower than if it's red light at 200 lux, because the response of that lux meter is much different for red light than it is for green light. That's just one note to make sure that you understand that lux, it does not directly correlate to power output of a panel. You would want to make sure that the lux that you're reading is for the spectrum that the panel is rated for. But again, it kind of gets a little bit confusing, so I mean, definitely reach out if you have questions, and then we can help you walk you through and make sure that you understand the power generation available in your environment. I wanted to go through and talk about PV lifetime. So again, when you're talking about energy harvesting applications, the end of disposable batteries, you want to make sure that you're replacing the disposable battery with something that can last a long time. So the good news is that you can easily achieve really, really long lifetimes with solar and solar energy harvesting. You just have to make sure that you are using the right protections and you have the right materials. So lifetime is going to be mostly dependent on a couple of degradation mechanisms. So number one, if you're in an outdoor environment, that's going to be UV exposure. So you can use UV blocking encapsulations. A lot of our panels, we use a UV blocking laminate that will protect the module from the UV. Also, if you have a device and then the panel is going to be integrated into that device, and you have like a clear window, just make sure that material blocks or absorbs enough UV to protect the panel underneath. Moisture is a big one. So protecting the panel from the ingress of moisture. So if a panel is exposed to, and it really doesn't matter what technology it is, some PV technologies are more resistant to moisture, less resistant to moisture. But really, if you allow excess moisture to get in around those electrode areas, around the contact areas, that'll start to corrode over time and can break down and reduce the overall lifetime of your PV. So making sure that the panel that you have is either in a well-sealed, weatherproof enclosure, or the panel itself has the proper sealing and the proper protection against moisture ingress. Another one is light-induced degradation. So this may seem a little bit counterintuitive that a solar panel actually degrade when you point it towards the sun, but it is something that you will see in some technologies. We have, for our amorphous products, there is some light-induced degradation that's also seen in some of the newer, novel, organic, and perovskite-based PVs. So on the right, I showed a chart of some of the degradation curves from light-induced degradation, because it's important to understand that for amorphous products, the light-induced degradation will only occur over the first couple hundred hours, and then it will stabilize and reach an equilibrium point somewhere. And also important is to understand that is from cumulative hours of direct sun exposure. So when you are talking about installing PV cells in lower light environments, heavily shaded outdoor, indoors, that light-induced degradation is greatly decreased and nearly goes away altogether. On the bottom right, this was a recent paper on the lifetime of organic and some of these newer novel PV designs. They suffer from that initial light-induced degradation, and then since these are newer technologies with many different configurations, the overall lifetime is very highly variable. So I mean, in this paper they cite anywhere from 2 to 6 years currently, going from after that initial decay, going from 100% to 80%. So maybe that can give you an idea of the current status of organic and some of these newer, very promising PV technologies. But again, long-term stability kind of remains a challenge for some of these newer PV technologies. And then another note is that silicon-based and 3.5-based PV, some of these they have a little bit more inherent long-term stability. So some of the other considerations that you might have for your PV cell would be size, thickness, and flexibility. Allowing your device to be thin and flexible, that's something that we work a lot with just because of the nature of our PV material. And you can do some really cool things where all of a sudden you're not limited by a thicker, a rigid element. You can start getting into some really compact, low-profile electronics, some really cool things going on in like wearables and portable electronics. So that's something that I get really excited about. And something that a lot of people don't think about right away, or maybe like a secondary thought, would be mounting and wiring. But it's something that you should really consider very early on. You can get a PV cell in most any shape or size or form factor, but it's going to have to integrate into your product somehow, both electrically and mechanically. And that can be a challenge that has to be overcome. So when we're talking about adhesives, glues, conductive epoxy, soldering leads, different tapes and laminates, closures, surface mount technology if you would like to mount a PV cell directly to a PC board or a flex circuit, different substrates. So a lot of our customers put our PV cells directly on fabric or plastic or metal. So we can definitely work with you to make sure that the mechanical and the electrical setup it works for your application. And then the last comment about automated assembly. I mean, when you go into production, to make sure that that you're able to manufacture these in a viable manner. Power generation. So I mean, this has kind of been a theme throughout this whole presentation, but just to understand the performance of your PV in your environment very early on, and then use that to drive your design decisions. So you might be calculating your power budget like Sarah described, and then maybe since you know that your PV is only going to produce this much, maybe you can use that to drive the design decisions of your product instead of turning on and sending data once a second. Maybe you wait a couple minutes, and that can have a huge impact on power consumption. So it's very important to understand the environment that you're working in and what you can expect for PV performance. Finally, cost and volume. Understand that you may be able to find a PV solution that satisfies all of your performance needs and your performance metrics, but it may not fit the cost metrics of your application. So there's always trade-offs between cost and benefit, and then scalability of the PV solution. Some PV technologies are maybe more in the R&D phase, so making sure that whatever you're using is the availability of whatever you are going to use meets the needs and the requirements of your application and project in both the short term and the long term. And I would like to finish with this slide, and this is a tool that we created. It's called the Custom Solar Panel Design Tool. So we kind of quickly realized that I understand PowerFilm's processes and manufacturing capabilities, but it's really hard for us to describe that and teach other people how we can make a custom panel. So we said, well, hey, we could make this tool, this interactive tool where people can go on and they can make custom panels for themselves, which has been a huge success. We've had a lot of people that have been able to use this to create a custom design on their own. They don't even have to talk to me, which is sometimes a good thing. But I'm not sad about that. So you can go in and do things like change the number of cells on the panel. You can change the size of the cells, change the length, the width to get the right shape that you want. You can compare. You can see how that changes the expected power output. You can change the operating environment, so you can select a standard outdoor panel or an indoor panel, and you can see the difference between power output. You can select a lot of different options. We list a couple of different popular options like backside contacts or cosmetic options. There's this, it kind of gives you a really good idea of what's possible for a custom design. I mean, again, IoT is a very, very broad kind of category, and there's thousands of different types of devices, and there's not really a one solution fits all. So it's important to understand that you can get a custom solar panel that's designed for your application specifically. I think we flew through this presentation very quickly, but it's all very good content. Thank you guys for attending. Please reach out to us for more information. If you have any applications in energy harvesting, we would really love to help you guys out and learn more about your stuff. I think Katie's going to come back on and handle the Q&A. Thank you.
Yeah, thank you so much, Sam, and thank you, Sarah, too, for your great presentations. So we do have a ton of questions that have come in from our attendees. Should a standard or indoor panel be used in heavily shaded outdoor environments? And Sam, I think that one can be for you.
Hi, yeah, great question. A solar panel, the right formula to use, so PowerFilm has two formulas. One is indoor, and we typically say that if your application is under 10,000 lux, we would recommend an indoor panel. If it's above 10,000 lux, we would recommend an outdoor panel. But really, a lot of times it's case by case, and a lot of times it depends on exactly how you're using the panel. So if you have any confusion as to which technology you should be using, just please contact us, and we'd love to go over your application specifically and figure out the best thing for you to use.
Okay, Sam, thank you so much for that first answer. Second question here, Sarah, you can take this one, I think. Can I use the AEM 10941 for EH and directly supply my electronics?
Yes, so indeed the AEM, it's made of a boost, which will be boosting the energy from the source. So here the power, the PV cell to a storage, which could be a rechargeable battery or a supercap. And internally you have LDO, so linear converter that you can use to directly supply your electronic, being sensor, microcontroller, radio, or anything you would like to use for your device. You can directly use those regulated voltages. You have up to 2 options. You can either use 1, 2, or none of that if you already have everything, or the DC-DC converter you would like to use. But this is an option, and the AEM can actually replace your entire power system now made of DC converter and the battery. So it could be a great option to take care of supplying your system, and also take care of energy harvesting as it best.
Okay, Sarah, thank you so much for that answer. For all our attendees, if you have a question, go ahead and place it into the Q&A window and click submit. We will do our best to get through as many questions as we can today. So guys, next question. Do solar cells change their power curves as they age or if they get dirty? How is that handled?
Yeah, I can answer this question.
Yeah.
If you go back to this, or if you look at the slide that I talk about intensity, so a dirty solar panel, if you get dust and debris on it, the only thing that's going to do is reduce the amount of light that reaches the panel. So if that's 50% reduction in light, then the power curve will reduce by 50%. Like Sarah mentioned, that reducing the light intensity could shift the power curve or the max power point tracker. With the AEM, it's able to kind of track that change and make sure that the panel is held at its maximum power point.
Okay, Sam, thank you so much for that answer. Next question here, guys. We are using an AEM 10941 and a proof of concept for an ultra-low power sensor. We have a large 5V supercapacitor and a 3.3 volt lithium primary battery. Right now, when the board is assembled, it takes a very long time for the board to start up, while the supercaps are charging up for the first time. Is there any way to configure the AEM to start up immediately and let it supply power from the 3.3 volt battery while the storage supercaps are charging?
Well, I can answer that. Well, actually, if you look at the way the AEM works, it needs to get to the normal mode, which means that it needs to get on the storage charge up to recharge ready. So there is a way to maybe accelerate it. I think maybe the best is to come back to us and contact us directly, because we already did it for customer. There is different option, and I think the best is to discuss, but there is a way to optimize actually the way it gets started. Just one thing for other device or design, what we need to get the LDO activated to get charge up to recharge ready, but those the overcharge, recharge ready, the over discharge, they can be defined by the configuration, so by the table you see here, but you see that you have the custom mode option where you can define your own level. So you could get the recharge ready lower than what it's actually defined by the 7 predefined mode. So there are options and there are ways to optimize, and I think the best is to contact us for further support.
Okay, thank you so much for that answer, Sarah. We have a lot more questions coming in, so we will do our best to answer all of the questions today. If we don't have time, we will get back to you following the webinar. So next question here. What is the light level or type of environment where your standard panels, like the LL200-3-37, practically start working with EPs? I am thinking of using it in a very low light levels with sensor signals transmitting only one time per day.
So maybe I can start and then Sam, you can follow. But to start the AEM, what we need is 3 microwatt, 380 millivolt. So based on the light condition, but it could be 50 lux, like Sam mentioned. At that level, I think we get enough power and voltage from the PV cell. Then the AEM will get started. It will get the energy all the time, and if you only need to transmit one time per day, then you just have to size correctly the storage. But I don't see any reason not to do it with PowerFilm and EPs.
Yeah, I would agree with Sarah's assessment. Definitely the LL200-337 form factor at 50 lux. We only guarantee performance down to 200 lux, but it still will produce power at 50 lux. And if that's a hard requirement for you guys, I mean, PowerFilm is definitely willing to work with customers on guaranteeing performance even lower, or at least exploring those options. So I would assume that it would turn on in that 50 lux kind of range, which is maybe what you would see in a dimmer warehouse or like a residential housing or a dark corridor. So if that's kind of the light level that you're expecting, I think that there's definitely room to kind of explore and see what we could come up with.
Okay, guys, thank you both so much for your answers. Next question. Are AEM PF EVK kits coming to the usual suspects soon? Examples like Mauser or DigiKey.
I could take that one, Katie. This is Joe. Yes, Mauser will be getting that kit on their website soon, but right now, as I think was mentioned in the presentations, you can get it off of the Power website, and actually I think we have a link to it on the EP's website also, but we are working with Mauser to get it up there, and I suspect within a week to maybe 2 weeks, they'll be selling it on their website also.
Okay, great. Joe, thank you so much for that answer. As a reminder to the attendees, if you have a question, go ahead and place it into the Q&A window and click submit. As I mentioned a few times, we do have a ton of questions in here. We will do our best to answer all of them today. If we don't have time, we will get back to you following the webinar. So Sam and Sarah, next question. How does a SI compare for power generation to DSSC in an LED indoor lighting environment?
Sam, I'll let you answer that.
Which question? Sorry. Can you repeat the question?
Okay, repeating the question. How does a SI compare for power generation to DSSC in an LED indoor lighting environment?
Okay, I found it. Yeah, so there's a DSSC I would consider to be one of the newer, more novel kind of PV technology. So it really depends on your manufacturer and kind of what they rate. In the lab, they've reported efficiencies into the 30% range. So it could be a little bit higher performing than our amorphous panels if you want to do a direct comparison. But really it's going to be dependent on where the source of the cells and then what the manufacturer is able to rate. So I guess that's probably the best answer that I can give.
Okay, thank you so much, Sam. Next question. The support battery has to be a primary, or can it be rechargeable?
So the primary battery that you can connect to the AEM as a backup solution, it will be sold by the AEM as a source. So it could be a primary or a chargeable one. The only thing is that the AEM won't take care of recharging it. So the AEM will take care of taking the energy from the harvester to the storage element, the rechargeable one. And if we achieve the minimum level on this storage element, which is the rechargeable storage element, we will use the primary as a backup solution. So you can connect anything you want, but just keep in mind that it won't be recharged by the AEM. It could be recharged by USB or anything, but it won't be by the AEM.
Okay, Sarah, thank you so much for that answer. We have lots more attendee questions, so we will do our best to get through these today. Next one, do you have any experience powering low-RON applications? If so, can you give more details?
Yeah, so actually we have built up some demo kit with Bluetooth connection, Bluetooth communication, but also LoRa or Sigfox. So we have some demo kits, some kits we use on trade show. Unfortunately, I cannot invite you to any trade show soon, but this is something we can show you, and we have some experience. What I can give you as details is that for now, what we achieve with PV cell is that we can send the messages to SF7 power output each 6 minutes. Of course, if you want to use the SF12 power output, then you might have to send a message each 30 minutes. But I mean, this is all about energy balance. So this is something well achievable. This is something we saw at customer application. If you go on our website, you will see some example and some customer design using LoRa or other other radio, but it's not an issue. So also please take maybe contact with us and at Joe or at support at eps.com, and we'll be glad to show you some examples.
Okay, great, Sarah. Thank you so much for that answer. Next question, what are some of the base polymers used for PowerFilms? What are the characteristics required?
So PowerFilm is actually not organic based. It's amorphous silicon, so it's silicon based, and some of its characteristics would be kind of temperature resistance. I mean, it's kind of inherently stable. So some kind of the same characteristics you would see on solar that you crystalline solar that you'd see on your rooftop will be similar from a material perspective. Some of the laminates that we use to encapsulate the solar cells and the modules are polymer-based. So it might be a PET or an ETFE, just depending on your application and if you need UV resistance or weatherproofing. But yeah, we work with the customer to determine the best encapsulation and then the characteristics required of the solar cell itself.
Okay, great. Sam, thank you so much for that answer. As I mentioned before, if you have a question, go ahead and place it into the Q&A window and click submit, and we will try to get to your question today. We do have time for a few more. I'm going to go with this one here, and forgive me if I'm saying these incorrectly. How does power generation graph look for fluorescent spectrum for GAAS, C-SI, and A-SI?
Yeah, so if you look at the curve for LED, the curve for fluorescent will be similar. And if you contact us directly, we do have a graph that does show the comparison for fluorescent, but to spare you guys a million graphs on the page, I selected these two. But yeah, it'll be, since the fluorescent and LED have light, or both have similar composition. I mean, the fluorescent is a little bit narrower in some areas. The overall performance, at least for amorphous silicon, will be similar. And I would assume that the performance of crystalline silicon and gallium arsenide would be similar as well. Thank you.
Okay, Sam, thank you so much for that answer. Next question, guys. Can the cold start time of the AEM 10941 be reduced with supercapacitors? For example, by using a small capacitor and a large capacitor that is switched on later?
Yes, of course. This is something we already did. So as you need to go to a certain level on the rechargeable storage, if you use a smaller supercap or a capacitor, you will get faster to this recharge ready level and you get everything activated. And then you could switch a bigger one that could be controlled by the AEM or something controlled by your system or microcontroller, you know, with some switch in between. This is something that we already saw, and this is one way to get your system or the cold start time reduced. And this is also something we can discuss if you can contact us directly. It will be easier to help you and help you moving on with your device design for it.
All right, Sarah, thank you so much. We do have time for, I'm going to say, 2 more questions today. So we're going to do 2 more questions, and then we're going to have to wrap the webinar up. Again, if we don't get to your question today, we will reach out to you following the webinar. So next question, guys. Compared with solar panels, what is the cost and efficiency of this AEM system?
I could start with that one, and maybe someone else might want to add in. But I'm not sure exactly the nature of the question. You're asking for the cost of the AEM device or the whole system? Because as you know, to do the complete energy harvesting circuit, you need the solar cell, you need our device, the AEM, you need a storage element, and then there's actually some discretes that are also included, 7 discretes, 5 capacitors, and 2 inductors. So the complete cost can be below $2 if you're talking about millions of units, or it could be $7, $8, depending on, for low volumes or for different types of the PV cells. So it's a hard question to answer without pinning down more details. If you'd like to contact us separately, we can give you specific details on some of the costs involved.
And maybe just on the efficiency.
go ahead.
Maybe just on the efficiency, sorry. The efficiency of the AEM, so it's a boost converter internally inside, in between the source and the storage, and efficiency could go up to 95%. So efficiency of the full system depends on the PV cell, the storage, and the voltages you need to supply, but those are, we can always optimize to achieve the best, and as Joe mentioned, feel free to contact us.
Yeah, this is Kip. I would just say from the film perspective, it's really going to be about the size of the panel. The price is pretty linear with size, depending on maybe how you do the contacts or specific encapsulation. You know, 5 to 10 cents per square centimeter is a good ballpark.
All right, guys. Everybody, thank you for that answer. So as I mentioned, this is going to be the last question today. We're almost out of time, but we're going to squeeze this last one in. If we didn't get to your question today, please do not worry. We will reach out to you following the webinar. So guys, last question. What is the maturity level of the AEM 10941 IC, and what is its life cycle? Would it still be available in a few years, or will its replacement be pin compatible?
I can tackle that one. This will be a quick one. So this is this device has been shipping in production for over a year. It's early in its life cycle. It will be available for many years, but there will be enhancements to it. For example, we'll be shipping a device in a CSP package, a chip scale package, which obviously won't be pin compatible. But we have a pretty aggressive roadmap, and if somebody is interested in hearing more about it, we can sign an NDA and give you some of those details.
Okay, thank you so much for that last answer. So as I mentioned, we're going to wrap the webinar up right here. I want to say a huge thank you to Sam and Sarah for their great presentations, and also to Joe and Kip for joining them today, and for everyone for taking time to answer all of our attendees' questions. So Sam, Sarah, Joe, Kip, I want to say thank you all for being here.
Thank you so much, Katie.
Yep, thank you.
Thanks. Bye-bye.
All right. And a huge thank you to all of our audience members for being a part of this webinar event as well. Take care, and we will speak with you soon.